Now let's go to angular momentum. That's the symbol for angular momentum, and could be represented in this way. Angular momentum is a cross product of r, which is the radius, or the distance from the axis of rotation where we find a particle which is rotating, and p, right? P is the linear momentum represented by mv. Or when we substitute the values right here, we have mass times r times v, the velocity. Or using the moment of inertia, also could be represented. This is, one more time, the angular momentum is equals to moment of inertia times omega, the angular velocity. Okay, because we're dealing with different objects, we have, for example, this angular ring, we have this marble, which is the bullet, and we have this turntable, right, that help us to work with the angular momentum. Actually, we're dealing with conservation of angular momentum. Okay, perfect. For a disk, we have that this is the angular momentum is 1/2 mr squared for a particle. In this case, we have two particles rotating at that distance from the axis of rotation. It's gonna be mr squared. Also, we have the angular cylinder. I'm using this masking tape. And it's equals to mass divided by 2, right? The interior radius plus the exterior radius, both square. In this experiment, we have from the theory, when we use conservation of angular momentum, and it's going to be the initial is equals to final. What is the initial? The initial is going to be the momentum represented by the bullet. We have a bullet impacting this object, which is connected to the turntable. They stick together, and the whole system rotates with the same angular velocity. Great. So at the beginning, we have only this moment of inertia, and at the end, right, what do we have? Well, we have all the system, all the masses move with the same angular velocity, correct? So this is going to equals to moment of inertia for each particle, particle 1, particle 2, particle 3, particle 4 times the angular velocity. From here, I'm solving for this angular velocity. In this way, is equals to the initial angular momentum provided by the bullet divided by the moment of inertia for each object, right, involved in this rotational motion. Okay, and we represent this as the theoretical final. It's going to be the final theoretical final angular velocity just before after the impact. Perfect. Now let's create an experiment that help us to double check this this formula. And to do that, we use the definition for angular momentum for one revolution or one rotation. Correct? Is equals to 2 pi radians divided by the period. So in this experiment, we're looking for the period. When we know the period for one revolution, right? Well, we apply that time in this equation, and we find the angular velocity experimental, and then we compare these two to see how close we are. In this experiment, we have 3 trials, right? We have a stopwatch represented by or given by this cell phone, right? We have the stopwatch, and because this is not the regular stopwatch, as you can start from 0 and so on. Right here, the stopwatch is running, so we start the experiment at some time, and we look for the time for the turntable to make one rotation, and that's gonna be T2 or T final, and then the period, of course, gonna be the difference, right, of these 2 times. Let's do it 3 times, correct, and find that time. This is gonna be kind of fast. If you find that it's hard to find the T initial and T final. Well, for one revolution, we can make it for 2 or 3 revolutions. If we do this for 2 or 3 revolutions, we have to divide the total time, the difference in this case, by 2 or 3, depending, right, how many revolutions you are taking into account. For simplicity, we can take 1, right, or you want again twice, correct? This is initial position. This is 1, and this is 2, right? It's gonna be T initial and T final. And then if we're looking for the time only for 1T for the period, we divide the total time from this interval by 2. Okay, in case you want it in that way. Perfect. So we have initial velocity. The initial velocity is calculated for the bullet is 5.5 meters per second. Also, we have the masses. It's already measured, right? We have for the turntable is about 50 grams. M2, which is this object, might be 94 grams. M3, the bullet plus this mass is 6 grams. We have this mass right here because if we only one mass right here, we have that the system is kind of unbalanced, right? I want to make it balanced. Otherwise, we create kind of friction when the table is not even. That's why I'm using an extra mass right here, which is the same mass as about the same mass as the mass that is provided by the bullet, right? To have the equilibrium and avoid friction. Correct. Also, we have the distances for the radius of the lever arms for each object. For example, for the turntable, this is R1. For M3, from here to here, the same thing for M4, from here to there. Right, for the annular ring, we have R sub I, R sub B, and these are the values right here. Correct. So let's substitute the values on the theoretical formula and compare that value with the experimental, right? Once we substitute the period in each trial. Okay, let me show you now how work with this experiment. Okay, see you in a bit. Okay, let's go for the experiment. So we have the turntable. They're supposed to be rotating in this way or in this way, correct? This is, we use this point as a reference point. It's gonna be 0 initial time, and then let's say final time for 1 revolution. That's the period. One more time, start right here and end at this position. We have the stopwatch, correct? So we have time, initial time, let's say 5.2, and then the final time is gonna be 6.5, for example. So the difference is gonna be the time for 1 revolution. Okay, perfect. Let's do it. Let's try to create three trials, correct? Let's do it. Let's load the bullet with this spring game, and let's try to create the rotation. Okay, in this case it rotates because it's not balanced. We need this bullet to make the balance, but let's do it in this case. Perfect. So we have the first trial. Great. Now let's go for the second trial. Let's remove the bullet. Correct. Let's go for the second trial one more time. Let's load the bullet. Okay. Let's go one more time and try to create the second trial. It's right there. Perfect. And finally, the last trial. Okay. And we're done with this experiment. At least one must be below 10%. That's the purpose, because it's kind of Let me see. Okay, great. Okay, perfect. Now let's do the calculations and let's find the percent error. Great. Yeah, it looks a very nice experiment, and see you in the next one. Thank you. Bye.